clip is a demonstration of Faraday's law of electromagnetic induction and the Lenz's law. The equipment consists of a coil of copper wire, a ferromagnetic core extending out from the centre of the coil. The coil is connected via a switch to a 240 volt 50 Hz AC supply. There are several aluminium rings of different thicknesses. First, a simple demonstration of Faraday's law. A light bulb is wired in series with a second coil of wire. When the current is switched off, the bulb lights up. What's the explanation of this behaviour? We know that a coil carrying a current will give rise to a magnetic field. Faraday's law says that where there's a change in magnetic flux passing through a conducting loop or circuit, an EMF will be produced, causing a current to flow. So the bulb lights up. In this demonstration, it might not be immediately obvious that the magnetic flux is changing. But remember, our coil is connected to AC supply. The current flowing through is varying sinusoidally with a frequency of 50 Hz. So the magnetic field also varies sinusoidally at the same frequency. Now, for a more dramatic demonstration of Faraday's law and the effects of Lenz's law. When the current is switched on, the magnetic field induces the current to flow in the aluminium ring. Like all currents, this induced current will produce a magnetic field of its own. Now, Lenz's law states that the direction of any magnetic induction effect is such as to oppose the change producing it. So the direction of this induced magnetic field must be in opposition to that from the coil. The ring experiences a repulsive force and is launched into the air. We can easily show that the force launching the ring into the air comes from an induced current flowing in the aluminium ring. This time, there is a gap in the ring. It isn't a complete circuit, so no current flows. Now, what would you expect to happen if we repeat it?
Okay, we will
experiment with the original ring, but this time we call the
Okay, we'll carry on with our worksheet. Okay, this one summarize what we have learned previously. We are now applying what we have learned to solve problem. Okay. right? We were looking at a rectangular coil moving at constant speed V into a region of uniform magnetic field. Right? There's the coil of 1 turn. That's the length inside the field. That's the width of the coil. So this is a region of uniform magnetic field. So the area, this area is L times W. Flux, right? Flux in this area is BA and replace WL. Right? BA, replace the A with WL. And L is just your V times your, right? V times your time. So we can rewrite that. This is the equation of a straight line. Right? That's the gradient. Compare with the equation of a straight line, we can draw the, right? How the flux changes as the coil move inside the magnetic field. Right? Where it's outside, it's no more flux. As it enters, it increases. Then after that, when the coil is complete inside, the flux is constant. Right? Area doesn't change anymore. And as it leaves the field, the area starts to decrease again. Right? Decrease again to zero when it's completely outside the field. Then we draw the EMF using Faraday's law. Okay, any comment? Anything not clear? You are muted.
All right.
All right, Okay, let's look at this question. Two similar coil A and B, this A, this coil B, of insulated wire are worn on a soft iron core as illustrated in the figure. When the current from this battery in coil A is switched on and then off, the variation with time t of the current is shown in figure 6.2. That's how the current changes. Switch on and off. This is basically called self-induction, but you don't need to know that. On figure, draw a graph to show the variation with time t of the EMF induced in the coil B. Ken, how to draw the graph?
Yeah.
How to draw the graph?
One. Wait.
Right? B is proportional to I. So we use Faraday's law. Right? E is given by the gradient. So this part is very steep. This part gets less and less steep. And then this part is zero, horizontal. This part is zero. Okay. And then this part, right, if you treat this part as positive, this part must be negative. Okay, if you are worried about negative sign, which Cambridge doesn't really bother, you can turn this one upside down, this one down, this one up, if you are particular about that. Can anything not clear?
Okay.
Okay. When the switch is closed, it takes some time for the current to rise to the final constant value. This is for your info. That's why it has a shape this way. It takes time for the current to rise like capacitor. Right? Where you have this one is not in the syllabus, but anyway, for your info. As the current rises, the changing flux in the coil A produces an induced EMF that opposes the rise in current. And the current will go very fast. So the changing flux opposes the induced EMF opposes the direct EMF or direct current. So that's why it rises up very slowly. Okay, elliptical spring is clamped vertically. That's a spring. The free end of spring is attached to a sheet of this free end to a sheet of aluminum as illustrated in figure 5.1. An electromagnet is placed near the center of the aluminum sheet. The mass is displaced vertically and the electromagnet is switched off as the mass is released. The variation with time t of the displacement x of the mass is shown. So you should be able to read from the graph that is a minus cos graph and it's an undamped motion. Electromagnet is switched on and the experiment is repeated with the same initial displacement. Damped oscillations are observed. Sketch the new variation with time t of the displacement x of the mass. So how do you draw? Yep.
Smaller amplitude.
Throughout.
Yes.
What type of damping is this one? Like they damp, no? This is the exponential decay. So amplitude becomes smaller and smaller. Amplitude becomes smaller and smaller. Period doesn't change. Right? There's exponential decay. Right? Lightly damp. Right? Something like that. State Faraday's law of electromagnetic induction. We have done that again. Done that already. Explain why the oscillation of the mass are damped. Yep. That's a diagram.
Due to
Right? You turn on the DC supply. There's your flux there. Right? Aluminium is just a conductor. It's not ferromagnetic. So as it oscillates, it cut the field. So there's induced current in the aluminum sheet. So basically your mechanical energy of oscillation is converted to induced current. So that's why it's slightly damped. Can?
yeah.
Right? Moving aluminum sheet cuts the magnetic field, producing an induced current in the sheet, causing a force to oppose the motion. Mechanical energy of oscillation is converted to electrical energy in the sheet. Suggest how critical damping could be demonstrated using the apparatus of figure 5.1.
You can see the apparatus.
Say again.
Can I see the apparatus?
See the apparatus.
Okay.
Yep. How to have critical damping?
Uh, critical damping means like
Say again.
no oscillation, is it?
No more oscillation, no, it just displays and then it will come back to rest. That's critical
Oh yeah,
rating,
no oscillation.
no oscillation. You can either put this one in oil or increase the number of turns. Increase the magnetic field strength by increasing the DC supply until the sheet, when displaced, return to its rest position without oscillation. Okay,
Okay.
a coil of insulated wire is wound on the copper coil as illustrated in the figure. An alternating current is passed through the coil. That's alternating current. That's an insulated copper wire. That's a copper core. Heating effect of the current in the coil is negligible. Explain why the temperature of the core rises. Yep.
Resistance. Internal resistance.
What about resistance? What has resistance to do with you cannot you must explain step by step, not just because it has resistance.
Uh, what to say? Like
Non-uniform magnetic flux in the core is changing. The core is changing. Induce different EMF in the different parts of the core. Eddy current or
can I
induced
say
current form in the core, which will give rise to heating.
can
Right?
I say EMF turn into thermal energy?
Better to say current. You have induced EMF that produce the induced current. So induced current flow in the copper core, so produce heating.
It's just so it's electrical energy into thermal energy. Okay.
But the field is non-uniform. You must remember that the field is non-uniform. Okay.
Yeah.
Two hollow tubes of equal length hang vertically as shown in figure. One made of plastic. One tube is made of plastic, and one magnet. A and B are the same. The other is made of aluminum tube. Two small similar bar magnet A and B are held above the tube and then released. The magnet do not touch the sides of the tube. Explain why magnet B takes much longer than magnet A to fall through the tube. Yep.
Higher magnetic.
Say again.
Higher magnetic flux. No. Wait, magnet B takes longer to fall. Okay.
Why? Right? Basically, this is non-conductor, so there is no induced current. This part, as the field of the magnet start to change across the aluminum tube, there's induced EMF. So induced current flow in such a way that it have a opposing field. So the magnet is decelerated. Okay.
So is it like the repulsion force? Like the north repels south?
Same as we push a magnet into the coil. So if this is a north pole, this will be a north pole to repel it. So it slow it down. then completely
Okay.
complete inside uniform. So as magnetic force falls, the tube cuts the magnetic flux. EMF or induced current is induced in the aluminum tube, but not in the plastic tube. Eddy current causes heating of the tube, which energy taken from the falling magnet. So the magnet B has acceleration less than 0. Right? Basically, your mechanical energy is converted to electrical energy and heat. Okay, now
Yeah.
two coils
Teacher,
P and
what's
Q.
eddy current again?
Eddy current are induced current. It's not beneficial
Oh,
to us.
okay.
You don't need to. You can call it induced current if you are not familiar with eddy current. It's not useful to us. If it's useful to us, we usually call it induced current. Two coils P and Q are placed close to one another as shown in figure 10.1. The current in coil P is constant. The iron rod is inserted into the coil P. Explain why during the time the rod is moving, there's a reading on the voltmeter connected to coil Q. We insert a bar, if you insert an iron rod inside as it moves, you can see the induced EMF in the voltmeter. Explain why.
Current. There's current flowing.
When the rod is moving, iron rod moving in causes change in magnetic flux density. Right? This causes a change of flux density in coil Q, producing induced EMF. The iron move in, there's a change in magnetic flux. There's an induced current, a change in induced current there. Magnetic flux across the secondary coil Q. So there will be induced current in coil Q. Okay. Okay now. Iron is moving in, it changes the field strength or magnetic flux across coil Q. Okay now. Okay now. But it's not clear.
Yeah.
Okay, the current in coil P is now varied as shown in figure 10.2. Right? That's the current, how it changes. Right? Thing to remember is changing flux is proportional to current, Faraday's law, and EMF induced is equals to gradient. So how does the graph look like? On figure 10.3, show the variation with time of the reading of the voltmeter connected to coil Q for time t equals 0 to time t equals to t2. Yep. Right? Remember the B is proportional to current or proportional to flux. So instead of thinking of current, you can think of it as flux. Right? That's the reason why EMF is equals to gradient. So that's constant. That's negative. This is 0. Okay. How they give the mark? constant reading, either polarity it can be positive, can be negative, doesn't matter. Constant reading from time 0 to t1. Spike in direction at t1, is very thin, showing a large voltage. That one must be, this one must be greater than that one there. Opposite polarity, another mark. And zero reading from here. Okay. Okay, let me go over with you. Anything you want to ask about the assignment? You did very well, except you lose unnecessary mark.
Not really.
Not really, I go over with you lah, where the mark lost.
Okay.
You cannot see, let me know. Right? This one, no problem. Acceleration perpendicular to velocity. This one is a bit not fair lah, because I think the syllabus say uniform speed lah. So this is a transformation of energy lah. Greater speed here, lesser speed here.
Teacher, is this the assignment?
Syllabus has not changed that much lah, but I was surprised this type of thing will come out lah.
Oh,
Because
teacher,
it
do you give
constant
me this
speed,
assignment?
Say again.
Did you give me this assignment?
Yeah, I gave you this assignment.
Oh, really?
Yeah.
I received the other one.
You got other assignment, man?
Yeah.
This is the only one, right?
The what? The one I submit to you.
This is the one, no? Assignment one, not assignment two.
Oh, oh.
Okay. So the speed here is greater at x is greater than at y, no? So you are okay, decreases. Right? So basically, the centripetal force is W plus N, no? So the centripetal force cannot be less than W, no? If it's going to touching the loop, no? Okay, this one, yeah, no problem. This one also, you have no problem. Conservation of energy, that's all. The kinetic energy at here equals kinetic energy at here. Okay, since you have no problem, we won't bother about that. This one definition only, no problem. This one, no problem. They just want you to calculate. But it's important that you do not leave out the essential step. This one, you have supposed to memorize this formula. So they allow you. So this one is 1 mark, both 1 mark. Gravitational force provides centripetal force. And then this one is worth another mark. Can either see it separately or in the equation there. But you cannot write this equation straight away. Right? Cannot write this equation straight away. You will lose this mark and you will lose this mark. Okay? They don't require to memorize formula for this one. This one, okay. I think this one you have no problem now. Don't bother about that. This one also you have no problem. This one you have a bit of problem. right? There's your S1, S2, S1, S2. That's your D, that's your S. So that angle is given. Right? That's the radius from the Earth given there. So you just take D equals to S arc length because this angle is very small. Okay? Okay with that?
Yeah.
I go very fast because you already know that we got less than 7 minutes now. This one, you're okay, no problem. Calculate the angular velocity. This one, you lose another point, right? Centripetal force at point P is the same and equal to gravitational force between them, right? Gravitational force between both of them is equal to centripetal force. That is the point you lose. Other than that, you are okay with this one. Okay, I don't think we will bother about that anymore. Okay, let's do question in AC. Basically, it's easy to set electromagnetic induction because it can cover magnetic field, it can cover oscillation. That's the reason why it's a popular question to come out. Okay, let's do this one. A bar magnet is suspended from a free end of an elliptical spring. Okay, that's a bar magnet. One pole of the magnet is situated in a coil of wire. Okay, that's a coil of wire. The coil is connected in series with a resistor. That's a resistor. The switch is open. The magnet is displaced vertically and then released. The magnet passes through the rest position at time as the timer is started. The variation of time with time t of the vertical displacement y of the magnet from the rest position is shown in figure 3. There's a graph there. When your switch is closed, state the evidence for the magnet to be undergoing free oscillation during the time t equals to 0 to t equals 4 seconds. Up to here, 4 seconds. What's the evidence is free oscillation. Free oscillation means there's no air resistance. Yep.
Damping.
Say again.
Has some damping.
There's nothing about the damping. You observe from the graph only. Right? Free oscillation is no damping force. So the amplitude of the oscillation remains constant. Amplitude constant. That's the evidence. State with reason whether the damping after 4 seconds, right? 4 seconds is here, is light, critical, or heavy. Right? Sometimes
Looks quite heavy.
Light damping, no? Why? Right? They state with reason. They don't want to say light only. Amplitude of the decreases gradually, so it's light damping. Determine the natural frequency of vibration of the magnet on the spring. This one should be able to do that. Right? That's the period. 0 to here. Okay. So your frequency is just that. Okay. Any comment? Anything that is not clear?
Yeah, okay.
Explain why after 4 seconds, the amplitude of the magnet is seem to decrease. Yeah, you turn on the, you close the switch, it's slight damping. So how? Explain.
Is it because of the eddy current?
Yeah, but there's not, I think this is about 2 to 3 marks there, so you have to explain it properly. Right? Current is induced in the coil. No need to use eddy current. You're not familiar. Current is induced in the coil. As magnet move in the coil, current in resistor give rise to heating effect. This thermal energy is derived from the energy of oscillation of the magnet. Thus, mechanical energy of oscillation decreases. Mechanical energy converted to electrical energy as an induced current flow. So the oscillation start to decrease in amplitude. Okay. Anything not clear?
Okay.
Okay, you probably have one. Right? Less than 1 minute. Bar magnet is suspended vertically from the free end of a elliptical switch as shown. One pole of the magnet is situated in the coil. The coil is connected in series with a high resistance voltmeter. Magnet is displaced vertically and then released. Right? This electromagnetic induction. Oscillating magnet will cause a changing magnetic flux across the coil. High resistance voltmeter will measure EMF induced. State Faraday's law. Right? That one, nothing much. Right? So I didn't bother. Use Faraday's law to explain why there is a reading in a voltmeter. Okay? That one you should be able to tell me. Since we are running out of time, I give you all the answer. Okay? We won't have any
Yeah.
class on Thursday. We only have it on Tuesday. That's all. I think we are quite fast. Give me time to update my notes. Okay, any comment? We are going to
Teacher,
be cut off at any time. Anything you want to ask? Anything you not clear?
my dad pay one that 500 was for last month.
Say again.
My dad paid